Welcome to the Level 2 video on ordinary differential equations. In the last video, we were solving a first order system using elimination, and I mentioned that we're going to solve it in two ways. But before we do that, we have to introduce eigenvalues and eigenvectors. So, we're going to talk about the characteristic polynomial. The characteristic polynomial is the polynomial and specifically the left-hand side of the characteristic equation. Which is the following: the determinant of a matrix A minus lambda, which is an eigenvalue, times the identity is equal to 0. So the characteristic polynomial is the left-hand side of this. And in the 2x2 case, has a pleasant simplification, so it can be written in a particular form. And that's the eigenvalue squared minus the eigenvalue times the trace of the matrix A plus the determinant of A. So you don't actually have to calculate the characteristic equation. You can just write down this special form. And in case you don't know, where the trace of A is the sum of the diagonal entries. And the eigenvectors are the vectors V satisfying the following. So A is a matrix, V is a vector, lambda is the eigenvalue, and V is another vector. And we'll come to this more in a moment. But first of all, let's talk about matrix diagonalization. Okay, so a quick definition. So two n by n matrices, A and B, let's say, are similar if there exists an invertible matrix P such that the following is true: B is equal to P inverse times A times P. And another quick definition that we need is an n by n matrix, say A, is diagonalizable if and only if it has n linearly independent eigenvectors, and we'll call these v1, v2 up to vn, and these correspond the eigenvalues lambda 1, lambda 2 up to lambda n. In this case, A is similar to the matrix D, where D is the diagonal matrix with the eigenvalues lambda 1 to lambda n in its diagonal entries. D is equal to p to the minus 1 a times p, where P is the matrix whose columns are the eigenvectors of A. So P is this matrix where all these columns are eigenvectors. So let's look at an example of this. So example, calculate the eigenvalues and eigenvectors for the following matrix. (15 minus 35, 6 and minus 14. So our solution is solve the characteristic polynomial, so the determinant of A, let's call this matrix A, minus lambda times I is equal to 0. So the determinant of 15 minus lambda minus 35, 6 minus 14 minus lambda is equal to 0 is 15 minus lambda times minus 14 times minus 14 minus lambda, so let's put the minus out the front, minus 35 times 6, so let's say that's plus 210, equals 0. If we multiply this all out, we have minus 210 minus 15 lambda plus 14 lambda plus lambda squared plus 210 equals 0, which gives us lambda squared minus lambda, where we can factorize out 1 lambda and have lambda times lambda minus 1, which equals 0, which implies that lambda is 0 or 1. And now we have to solve the eigenvector equation, AV equals lambda v, where lambda was our eigenvalue. And we need to do this for both eigenvalues. Okay, so then we'll have two eigenvectors. So case 1 is lambda equals 1. We have 15x minus 35y equals x. This is just multiplying out the eigenvector equation. 6x minus 14y equals y, which implies that our first eigenvector is 15, 6. This is because either of these two equations, setting x to be 15 and y to be 6, would solve them both. And case 2, where lambda equals 0, we now have 15x minus 35y equals 0, and 6x minus 14y equals 0, which implies our second eigenvector is 14, 6. Again, if we set x equal to 14 and y equal to 6, both of these two will be satisfied. Thanks very much for listening.